So for people just coming back in, we're now going to use the files and stuff in that repository. So if you haven't downloaded it yet and you want to, you're not required to, you could just watch. But if you do want to do it on your own computer live, you can download that stuff. If you want to just watch and go through it later on your own computer, which is sometimes preferable for some people, you can download all the stuff afterwards. So totally up to you. Let me zoom in a little bit. Seeing as we do have limited time, if for people who haven't downloaded all the files, or if it takes you more than 5 minutes, if you're just like joining late, then we're not going to be able to wait like super long if you weren't. But everything is on this link, so you can look at it afterwards. You can look on with your neighbor. Do most people have this stuff? There should be trying to simultaneously. Can I move off of the link to a different screen? Oh, I put the slides in the repository, I think, so you could click on this link too. Or I remembered to upload them during the break. But, so what I wanted to do now is in that repository, if you've downloaded it onto your computer, there should be, you're not going to have all of this stuff, but there should be a project file here that if you're using RStudio, which I recommend you can use, if you're just using regular R, you can still open the markdown file, but I'm going to use the RStudio project. And then there's this pest control example file. I'm going to say a little bit about this before. There's a lot of stuff in this file. I commented out you'll see I commented out the entire second half, just to say that like we're probably not even going to get through the part that I left uncommented out. But there's also a lot of Stan programs in the folder called Stan programs, and they probably look intimidating and stuff like that. We're going to work on the simplest one that all the code isn't even there because I didn't give you the answer yet. But I gave you all the rest of the stuff so that later you really can uncomment out the second half of the document and run it on your own and follow it through to conclusion. But a lot of the files in there might not make sense until after you've done the hierarchical models part. But I wanted you to be able to eventually, because this is like a little case study that Lauren and I and Rob Trangucci, one of the other Stan developers, put together. So I wanted you to be able to go through the whole thing at some point, but in this workshop we're just going to cover the beginning of it. But all the stuff is in there for those of you who want to venture forward. And so, actually, yep. Before I do the code, do you want to take just a second and explain the setup of the problem?
Oh yeah, sure.
Because you know that, right?
Yeah, and I've got my cube.
And so what we're going to do is we have a little example here where we're going to fit a very simple Poisson regression model, like not a hierarchical model. And because I wanted to show you a different kind of outcome variable than in the linear model. But all the code related to that paper and the simulations in the slides that I showed you, there's a link in the slides to a GitHub repository where you can have all the code that was used to make all those visualizations and fit the models that are later on in the slides. So you can so I posted the slides. That link is on this slide. Oops. Down here. So all the code related to the first half of the talk is in there for those of you interested.
Cool. I've got this. It's okay.
Okay.
Can everyone hear me? Yeah? Cool.
So I'm going to let Lauren just tell you about the problem that we're going to work on.
Yeah, so we really wanted to give you a data set that we could share freely and you could kind of explore. So we and Rob sort of created an artificial data set, and so we were all in New York City, and so we thought, well, imagine you're a statistician and you've been called in to consult, and one of your clients is a manager of a bunch of residential buildings. And so the setup is that the manager is concerned that they're getting all these complaints for cockroaches, and it's kind of undesirable, it makes their buildings look bad. And so previously there's kind of like established methods of how no worries. Of how to manage pests in New York City, but there's this alternative method and of setting baits in the buildings and not in the hallways of the buildings. There's sort of bait stations. And so the question that we were kind of playing around with was, how do you know how many bait stations you should put in a building, and sort of what things determine how many you should put in? And so our outcome variable in this case is the number of complaints. So the number of complaints a building gets each month. And the setup is that, well, the pest inspector comes out every month, and at the beginning of month, he just sort of randomly allocates some number of traps. He's not very good, he just sort of goes out and he pops in some traps, and he doesn't really look to see how many cockroaches there are. So there's sort of, they're not related. And then at the end of the month, the manager comes to you and says, well, we had like 20 complaints this month, or we had 10 complaints, or we had 4. And the question is, how many traps should you put in each building to minimize the number of complaints, given that the traps are quite expensive and they cost money and these things. So at the very end of this sort of vignette, I guess you'd call it, we sort of do like a costs analysis. But for now, what we're really interested in is just sort of modeling the number of complaints as a function of the number of traps in the building and also some building-specific traits. And so the data that we have is quite rich. So for the very simple model, we're going to ignore quite a bit of the structure of it. So we actually have, which building the complaints are coming from, and I think we simulated 10 buildings, or 20? 10. Over 12 months. So we have sort of temporal data, and we also have clustered data. And so as you work through the vignette, you sort of see that we start to incorporate that information in, but as a very first pass, as Jonah was talking about a network of models, we're going to do just a simple Poisson model where we're looking at the number of complaints as a function of number of traps in the building. Are you going to put other variables in? If we have time, we'll incorporate other things like whether they have a live-in super, so like a live-in building manager kind of, the average rent, the average age of the building, all of these other sort of rich factors that we can include. So if you open your data set, and just by loading it in, and just take a look, you can sort of see that we have all these variables, and so the ones that are really important for us today is the number of traps, the number of complaints, and that's pretty much it, actually.
Those are the two big ones.
Yeah, and sort of as you work through, we start to include more and more of this information.
Right. Yeah, later on in the document, it starts adding in how do we build a model that it will include all the different types of information that we have.
Yeah. So, I don't know, do you want to take over and do the...
Do you want me to do the code?
Yeah, do you want me to, I don't mind.
You sure?
Okay. Yeah.
Okay, so this is what the document at the end, rendered version would look like, but in the file here, it's just kind of inline here. For those of you who are following along, I'm just gonna actually load these packages here. And so there's a lot of text in this file, and that's mostly so that when you look at it afterwards, you'll remember what the context is. You don't need to be reading all the paragraphs in depth right now. It's more just so that things that we say out loud, you can remember them later without having to take notes. Okay, so like Lauren said, we have this issue where we're trying to figure out how many cockroach traps to set in these buildings, and we're interested in this trade-off between having to spend more on solving the problem versus, solving the problem with some amount of cost, and we want to try to find the right balance between how much resources we put in there and how much we allow the problem to persist based on this decision problem. And again, so we're not going to get to that stage of the document now, but eventually later on in the document you see that the goal here was to be able to maximize the company's expected profit, or in this case it's going to be negative because they're not solving entirely the problem, the roach problem, but in this case, right? So to be able to think about expectations, how can we make choices that according to the model are going to maximize whatever we care about, which in this case might be some trade-off between saving money and pacifying the residents in your building, right? But you could imagine in whatever field you're interested in that for the most part, ultimately why you're doing all of this is that it's relevant to decisions, right? Whether or not you're the decision maker or not, or whether there's a decision that comes right after your analysis, most of what gets done is going to inform some sort of decision making, right? And so towards the end of this document, you see how can we sort of use these models to think about decision making. But the first step to doing there is to figure out how do you start coding these models. And so what I want to do now is code up the simplest model we could think of for this data, which will not be a hierarchical model, which will just be a simple model for the number of complaints as a function of the number of traps, even though we have much more information on that. But that's where we'll start, so that we'll introduce Stan coding. For those of you who want to follow along, I'm gonna do some live coding here. I'm gonna take that chance. But the first thing I'll do is I want to show you just visually quickly what some of the data looks like. And so if you are doing this on your own computer, you can make these plots. But this is across all the data, we're just aggregating up all the number of complaints from the residents about the pest problem. And you can see that there are some pretty extreme complaint numbers there, but most of them are clustered down there. There are, one thing you see in the rest of the document, there's more zeros than we might expect from a Poisson distribution, and so some of the rest of the document goes through how can we account for that, and right? But to start with, and even if I already thought that this super simple model is not sufficient, usually I'm gonna start with the simplest model I can think of, and then interrogate it and figure out what is it not sufficiently capturing that is important. Instead of starting with the super complicated model that I think of, which then if that goes wrong, it's much harder to figure out why it's going wrong. As the document shows, and what I would do in practice would be to start simple and keep adding the complexity that I think makes my model more and more realistic, and at each stage checking that that has the effect that is intended, right? That things don't go haywire at some particular stage, that the results stop making sense, right? It's much harder to figure out what went wrong if you start really complicated. You're gonna make sure that at every stage along the way, the results keep making sense. And so if after StanCon you're going through the rest of this document, that's the process that you're gonna see. The models keep getting more and more complicated. And even though I've been doing this for a while now, I still do things that way. As Ben Bales here, one of our Stan developers who takes a lot of risks on the forum and tries to help people with models even if he doesn't understand them. It's kind of scary, right, when people ask us questions about models that are outside of our, we're trying to help figure it out, and none of us want to look stupid, right, but we still try, and And when people ask questions, right, and Ben is often risking himself and trying to help people with these super complicated models that the rest of us are like, oh my God, it's going to take me all day to read this code and figure out what they're trying to do. It's much harder to help someone figure it out when they haven't gone through the steps along the way to make sure all the choices that they're making have made sense. And just looking at like a complicated model and someone saying this is going wrong in some way is really difficult, which is why you do that more than I do. Sorry, I didn't mean to call you out down there. And then you can see that this is a time series. Later in the document, it deals with time varying components, but we're not going to do it in our part. So we have different buildings and different numbers of complaints by month. And then the number of traps also varies, which is the dashed line. And so you could see that it might, it's kind of exploratory data analysis. I'm not really looking too closely at like what's actually happening in each particular building and memorizing this, but there is some time component to this that we'll see eventually. But has everybody here familiar with the Poisson distribution? If not, it's okay. All you need to know for our purposes here is that it's pretty much the simplest distribution to use when your outcome variable are counts of things and there's not some known cap to that number of things. So right, in this case, the number of complaints could theoretically be unbounded, right? It's going to have, practically it won't be, but, right? So the Poisson is the simplest choice to make in that situation. And so this is the model we're going to write down in Stan in like 2 minutes. That the number of complaints in building B, I'm just indicating, using B for building at time T, I guess I could have used M for month, has a Poisson distribution with rate parameter lambda. So that's like the bigger lambda is the mean and the variance of the Poisson, right? The bigger it is, the more complaints we expect. And because that has to be positive, right, if you've heard of these ideas of link functions and inverse link functions, we can't, if we want to do some regression on something that's not necessarily positive, right, we have to do some transformation to pass it through like some transformation that makes it positive, right? It doesn't have to be using e to the whatever, but that's the most common one for the Poisson distribution. This is like kind of the same thing in like a logistic regression. It's the logit and inverse logit, and here it's log and exp. And then here's just a little linear regression here, right? An intercept, a slope, and then the number of traps. And if you notice here, there's no indexing on the alpha and the beta. So this is not like, there's no variation by time or by building in the parameters, only in the data. Later on in the document, it starts adding in variation in the parameters according to different things in the data, right? So we can index the data here, but the parameters are just, there's one alpha and there's one beta in this really simple model, like the first linear regression model in the slides, except here, that gets passed into this exp here, right? And so really, this is interpreted as being like on the log scale. Are people familiar with that kind of Poisson regression stuff? Okay. So, and then there's gonna have to be some priors on alpha and beta here. So what I'm gonna do is in the Stan programs folder, I'm gonna open up, now there's a lot of things in here to be able to run the later one, but I'm just gonna open up simple Poisson regression.stan. And it's gonna be mostly empty with some comments to remind us of a few things we wanna do without having to keep switching between files. So everybody who is wanting to follow along at the moment have this like somewhat empty simple Poisson model file? Okay. At the top, you can ignore this. This is just a temporary thing where occasionally you can get random numbers from a Poisson distribution that are that have numerical issues. So don't worry about this piece here. It's not really what we're here to learn. I just put it here so that we can use it and avoid some problems, but it's not really relevant to learning Stan, and it shouldn't be necessary as of like the next release anyway. It just helps us avoid some numerical problems if we get super large values. The important thing that I want to look at here is that there's a structure to this document already, right? Now, we would have to type this out normally. I put this here. I put this little template here. And you can see that there are these things that are like, within curly braces, there are these like kind of what we call blocks. There's like a data, parameters, model. There's other blocks too that are optional and that I'm not putting on here. But the important thing to notice is that there's this organization of the program into different blocks. And they correspond to the different pieces that we need to specify a model. We need to know what data we've observed, outcome variables, predictors, all sorts of things. We need to know the things that we want to make inference about. So what are the unobserved things that are relevant to the model that we want to learn about? And then we need to know how those things relate to each other. And that's what goes in the model. Right, so this might be, I have data Y and X and this many observations or whatever, and this might be, I have a slope and an intercept in the simple case, and then this might be, oh, they're related because those are part of the regression in the Poisson distribution or something. And so that's what we're gonna encode, and then down here, generated quantities is where you can use like the posterior distribution to like make predictions or whatever you want to do using the resulting estimates. So here is the model, and then here, assuming the model, what other things do you want to know about? Maybe I want to fit the model and then make predictions for new data or something, and that would go in here. And so we'll see. And then there's some other optional blocks that are less important that we can touch on if we have time. Okay, so Stan, unlike some other languages like R and Python, but like languages like C++, we have to use variable types explicitly. Now, in other words, if I want to tell Stan about an integer, I have to say int. So for those of you who want, you can type along with me. Otherwise, you can just look and run this later. So what I'm going to do here is tell Stan like the size of the number of observations we're going to give it. Right? So this data block maybe would be better labeled external data. That is, what data do we have sitting in our R session or our Python session or MATLAB or whatever interface to Stan we're using that we want Stan to eventually know about and be able to use? We're not going to like put the data here. We're going to tell it the sizes of those objects, what to expect when eventually we run the model. And then when we run the model, we're going to say, hey, connect it with these particular variables in my R session. And then Stan will check, well, hey, was that the right size that you told me it was going to be, that kind of thing. So in other words, if we want to tell Stan that we have like capital N observations, which could be 1,000 or 1,000,000 or something, right? I'm going to just call it N. I could do, this is what this line does, is it tells Stan that at some point, or not at some point, like immediately when I hit the command to run the model, I'm going to be feeding it a value for N, and that value will be an integer. Now in our case, it's going to be the number of rows in the PEST data set. This is just telling Stan, okay, here's the number of observations. By coding it as N, I can use the same program with 10 observations, 1,000 observations, 1,000,000 observations. All I need to do before I run it is associate the letter N with a particular number. And we're going to do that from R when we say, hey, run the Stan program, we'll tell it what the value of N should be. right? And so this is a way, now I don't have to call it n. I could have called it anything. I could have called it tomato or something. It doesn't matter. It's just eventually you need to associate with that some value from R or Python. And so in our case, eventually we'll tell Stan that n is going to equal the number of rows in pest data. So eventually, in our case, n will be 120, but it could be something else. Does that make sense? All we're telling Stan is be on the lookout for an n that's an integer. If I wanted Stan to like complain at me if I passed a negative number, a negative integer for n, then I could add a little constraint here that says, hey, that, in this case, maybe I have to have, I don't want to use this unless I have one observation, at least one observation, right? If I tell you n is negative 20, then don't even try to run the program, just tell me I'm an idiot. And that will, so what happens, you'll get some message out that says n is supposed to be greater than 1, but the value is negative 30 or something. So these are just sanity checks. If there was an upper bound, I could do upper equals something. So that, and in the data block here, these sorts of constraints are optional. It's just, hey, Stan, check for me when I feed in the data that what I told you it was going to be is actually what it is. Okay. Now, the reason I put this as the first line is because the next thing I want to do is tell it that I have like data that has n observations in it, that I have some variables that I'm going to give it n values of. And before I could do that, I needed to tell it, I needed to give it n. So in order for me to declare something of size n, first I need to declare n. And just say, hey, n is going to exist. Now, whatever value it is, right, I don't need to know right now. I can just say, now let me declare that there's going to be something that's of size n, right? And so, for example, in our case, the number of complaints, right, that we have in the data set is also an integer. Well, it's many integers, right? It's like there were 10 complaints or 13 or 0 or something like that, right? And so, oops. In that case, the smallest number of complaints could be 0, right? Again, this is just going to have Stan do a sanity check here on us, that we don't tell it that there were -2 complaints in one of the buildings. And just to be, right, and then I'm going to call the variable complaints, but we could be general and call it y or something for the outcome variable or whatever. And then I'm going to say, okay, there's n of them. We'll see in a second that there's a difference between whether we put, in some cases, you're allowed to put that size in different places, and we'll get there at some point, and I'll explain the difference. But for now, this is how I tell Stan that I'm going to give it an array of integers, and there's going to be n of those integers in it. Now, in other words, this is sitting in R. It's one of the columns of that data set, right? The complaints column. And then before we run it, we're going to use the command from R to run the model. We'll say, okay, the complaints variable corresponds to that column of the data set. But right now, we're kind of abstracting away from the actual data and saying, well, how do we just express the probability model? Is there a question on this side? No? You good? Okay. Now again, you don't have to memorize all this syntax and stuff like that. The point here is to get slightly familiar with it. For some of you, it'll help to have the rest of the conference not be mystifying when you see bits of Stan code, just to kind of know that, like, hey, this is kind of what's going on. There's, you know, I don't ever write a Stan program without some sort of syntax mistake. So like, you're not going to learn how to write a perfect Stan program today, but I'll show you how do you figure out what mistake you made. When we write some lines, we'll see that like it'll complain at you in certain ways. So the goal here is not to write perfect Stan syntax, it's to get enough of a feel for it to figure out what the mistake is. Because I'm always going to make mistakes too. Okay, and so there's only one other thing that in our simple model here we're counting as part of the data, which is just the number of traps that were there, right, in the building at that time. And I can even just copy this line. I mean, I could retype it out, but it's really the same line, but it's for traps, right? Now, I kind of tricked you for a second and got you to type this for practice, but now I'm going to tell you to change it in a second, just to illustrate a point, because, so what did I say here? I said here that that complaints were an integer. Now, in principle, we could treat like these integers as real numbers, right? Because 1.0000 whatever is the same as 1 as whole, right? Whole numbers. But when we go to use the Poisson distribution in Stan, it knows, okay, this is defined for integers, right? For counts, and it will complain at you if you didn't declare them as integers, if you declared them as like real numbers or something, right? And so that's why like we have to declare the complaints as an integer. We have more flexibility with traps here because it's just going as an input to the distribution, right? There's no necessity that it has to be an integer or a real number or anything like that. That's only for the outcome. And so since traps is going to be an integer, this is a valid way of writing it, but I want to show you to make this point. So I'm going to comment out this line. I want to write, instead of int, I want to write this as a vector, and so that I can have a chance to explain what this distinction is. And again, this lower equals 0 is optional in the data block. It's just going to complain at me if I tell it there were -6 traps. Now, here, I'm going to put the n here. And now you're probably thinking, what kind of moron designed this language? And in fact, it wasn't a moron. It was a very clever guy named Bob, who you'll hear from at the conference. And the reason is because I could also do something like this. Or this could be another letter, a variable, right? What that means now is that I'm telling Stan to expect 3 vectors of length n. Right? In other words, I'm going to give you an array that has 3 objects, and each one of those objects is a vector of length n. And so the reason, and so this word vector implicitly means a vector of real numbers in Stan. And that's because we use the term vector, matrix, real, to define real numbers, because those are what you can do linear algebra with, right? So like, if you call something a vector in Stan and something else a matrix in Stan, then you're going to be able to do traditional vector matrix operation, linear algebra operations. For things that are integer types, not just whole numbers, but like the computer is classifying them as an integer instead of like just a whole number, then we have to use this alternative syntax, which is just an array. We can't do linear algebra with just like a container of integers unless we declare them as real numbers that just happen to be whole numbers. And this is a little bit of a subtle distinction here, but it's one of the biggest points of confusions I get when teaching Stan, is just what's the difference between an array and a vector in Stan. This is the syntax for an array of integers, and this is a syntax for a vector of the same length. I can do linear algebra with this. I can't do it with this. Think of an array as just a box, a generic container. I can't multiply a container by a matrix, right? But I might be able to multiply the component, like the things that are stored in that container by a matrix, right? So if I had here, this is now an array that contains 3 different vectors of length n. I could multiply each of those vectors by some matrix, but I can't multiply like a container by a matrix, right? So that's the way to think of an array, as just some generic container that it can contain matrices, it can contain vectors, it can contain integers. It's just a generic container. It's useful for storing complicated data structures. But if you want to multiply things like you're used to, like vectors times matrices, things like that, then you have to use declare them as a vector or a matrix or something like that. That's basically all you need to know about that distinction. Now, if you ever run into situations where you're fitting models and you wonder if one way or another might be more efficient, then you're kind of already at an advanced stage. Question.
Could you say what is the number of bytes in the real data type?
What is the actual value of n?
So the data type is real of this vector, as you said, and what, how many bytes are in this real?
That's a good question.
32 or 64?
Do you, we're 64. What, Ben? Do you know how many bytes? The vector. Yeah. Okay, we can get you the answer to that. Ask Bob. It's all in doubles, double precision.
Okay, double.
Definitely.
Okay, thanks.
Then there's some other stuff tacked on there that Bob can answer. But yeah, we're doing everything in double precision, and that's actually important for the algorithms underneath. Okay, that is the complete data block because this simple model is using nothing else, right?
So Jonah, why would you want to use int, like containers of ints rather than vectors? Like what are...
Here?
Why would you want to?
Well, here's, like I said, it was because the Poisson distribution will complain at us if we use an outcome that's not actually declared as an integer, because the distribution knows, hey, I'm only allowed to be used with non-negative integers. Whereas for traps, it's not the outcome variable, and there's no necessary thing that like predictors have to be non-negative integers in a Poisson or something like that. So I have more freedom with how I could have declared traps as an integer. I have a little more freedom there than I do with the outcome variable. Other questions at this stage? In the back, can you yell or do you want the box?
But will the recording pick it up?
I'll repeat it. Yeah. It has to be checked at runtime. So the question is the lower bound thing checked at compile time or runtime? So you can compile this without ever telling it what data you're going to use. Only once you associate it with the data set and run it can it check like, oh, you actually gave me the right kind of data. So like it won't know that n has this value or it satisfies this when it's compiled, but it'll know the minute I tell it what n is. Good question. All right. The nice thing about this is the parameters block is basically, is very similar to the data block, except we're just declaring the things that we don't know, but that we want to know, right? In other words, in our case, we just have that alpha and beta, right? So just like we told Stan like what type of variable complaints is and what size it is, we're going to tell it what type the alpha and the beta are and what size those are. And in this case, it's easy because they're just both single real numbers. But you can use the more complicated data structures if you have more complicated model. You can have arrays of parameter vectors. You can have arrays of covariance matrices that are parameterized, right? The parameters block is performing this same function here. So now we'll see for the first time, what do we want to do if we have just one real number, a scalar number, right? We could, to do that and to just declare a single scalar real number. Now there could be a vector of size 1, I guess. But we can also just do this. We say, hey, I just have a real number, alpha, right? But because I put this in the parameters block, I'm saying, but I don't know what that value is and don't expect me to give it to you, right? Like it should expect me to tell it what these values are, but it's not going to expect me to tell it what's here. Here's I'm telling it the things that I want to learn about. And so Any brave soul know what the next line is going to be? I'm totally serious. Yeah, it's the same thing, but for beta, right? Yeah. Now, one thing that we don't have to do here that we would if we were fitting a linear regression, right? If we were fitting a linear regression, we'd have some like sigma parameter, right? And so I just want to take a second because neither of these parameters is constrained, right? These can just be any real number. If we had a parameter like sigma that, by definition, is not negative, right? You can't have a negative standard deviation. Then we would have to tell Stan that using that lower and upper syntax. And so just pretend for a second that in our model here, we knew logically, not that our prior was that it had to be positive, but like there was some like logical reason, like standard deviations can't be negative, that kind of thing. And we wanted to say that beta has to be positive. Now in this case, I wouldn't do this, it doesn't have to be. Then we would use that same syntax, but it wouldn't be optional anymore. It wouldn't just be a sanity check. And that's why I wanted to make this point here. The reason that it's not optional here is that the bounds here are defining the valid values of the parameters that you are performing inference on, right? If you want to, so this is essentially telling Stan what is the possible range of like legitimate values for all of these quantities. For the data, it doesn't matter as much because you're just passing it in. It's fixed, there's numbers, they're numbers. But here we have to say, we're gonna learn these, so we have to say, well, this is only allowed to be in this range. Like if you wanna learn a correlation, then Stan doesn't know that whatever name you give it represents a correlation. You're just calling it whatever you want, but you would put lower equals -1, upper equals 1, right? You're defining, like a correlation is bounded between -1 and 1 by definition, and so we would have to encode that there if we wanted to get valid estimates for a correlation. So that's why it's not optional in the parameters block, and in fact, one thing that often goes wrong is you'll forget to put a constraint. If you have a linear regression, you'll forget to put lower equals 0 on sigma. And thankfully, usually what happens is you get a lot of warnings telling you, hey, sigma is negative, that you're getting a negative standard deviation parameter to the normal distribution because Stan's normal distribution function will complain, right? But in our case, these are allowed to be any real numbers, but we're implicitly defining the parameter space, is what we would call it, right? What are the boundaries of the parameter space? So is that clear why it's not optional in this case, in the parameters block? Okay. This is a reminder to me. And okay. What time is it? 11:15. Okay, I think we're gonna get through this and then fit the model and be good. Okay, so the purpose of the model block in a Stan program, like I was saying before, is to express the relationship between the data block and the parameters block. There are optional blocks where you can transform data and transform parameters, and those would be included too. But the idea here is what is the statistical model that is relating the observed and the unobserved quantities in our model, right? So another word for data could have been observed, and for parameters, unobserved, right? And in a Bayesian context, that's exactly what data and parameters mean. Missing data are parameters because they're unobserved. So really, we might talk about data and parameters, but you can also just think of this as observed and unobserved. Anything that you don't know the value of, and you want to, or you want to, you're not going to know it exactly, but you want to estimate it, goes in the parameters block. whether or not it's a slope or a missing data point or something. Anything you want to perform inference on. And anything that you're going to condition on, as in, I want to use this information and learn from it to learn these other things, that will go in the data block. If there were constraints on beta, in this case, we're going to let it be any real number. But if we were in a situation where we knew logically it had to be positive, you would have to put the lower equals 0. Otherwise, it doesn't know what the valid values to perform inference over are. Other question? Yep. And so the question is, can they be hidden variables? Or yeah, anything that is unobserved. So any sort of latent variable stuff, anything that you're not going to tell it what the value is, right? Goes in the parameters block, which is why it's a little bit of a it should really say like unobserved or something. Parameter is a little strict in that sense, I guess, but there's really no distinction between those things in the Bayesian treatment. It's anything we have uncertainty, we're going to say uncertainty about, and anything we're going to treat as known, and that's the distinction that's relevant here. The purpose of the model block, right, I said is to express that statistical relationship. The way that you do it in Stan, or really what it's doing under the hood, is it's just tallying up. So you could imagine that for each observation, right, each one of our n observations is going to contribute something to the model, right? We can evaluate the Poisson distribution using that, particular observations data, and we get some number, and that happens for each of the data points, right? Like, in other words, we're indexing here, right? We could have for each building at each time point, right, we're going to evaluate, we're going to have this, right? We're saying that this is the model for all the observations. It's not that some of them are not Poisson or something like that, right? So each one of the, in our case, 120 observations is going to contribute something to the total, to the likelihood, right? And then we'll also have contributions from the prior, and together that's like our whole model, right? In other words, we can, if you remember back in my slide, right, and in Bayes' rule, you multiply the likelihood times the prior, but each observation has a contribution to that likelihood. And so if we then think here, so the model block, essentially, you could do each observation one at a time. You could do them all at once in a vectorized fashion. It doesn't matter as long as by the end of the model block we've arrived at the equivalent result. You could write out the math by hand instead of using named distributions that we have in Stan, and by hand I mean typing it into the program. There's all sort, like any language, there's many ways to express the same model, and the reason we know they're the same model at the end is that the total, in other words, the numerator to Bayes' rule, the prior times the likelihood, will be the same up to some constant that doesn't depend on the parameter. So any models that you define that result in that same are equivalent models, even if they look different, right? In other words, mathematically, if the numerator to Bayes' rule, the likelihood times the prior, is the same up to a constant for your model and my model, then they're the same model, even if I wrote them differently. I'm going to get the same inference, right? And so you can see, you'll see lots of Stan programs written in different ways that are specifying the same model because they result at the end of the model block in equivalent calculations. So the way I show you to write this is not necessarily the only way you'll see somebody write a Poisson regression in Stan, because it's a language like others. There's many ways to do it. And so we'll do the priors first. So these aren't, I'm not going to be, you'll hear lots about over the next few days in the conference, how do you think about choosing priors for different types of problems. So in order to get through this code a little quicker, we'll make some simplifying assumptions here. Right, so what is alpha? Alpha is the intercept, which means it's, right, when the number of traps is 0, then alpha is what's going into the, well, into the Poisson or the exp, and then into the Poisson. And so if there's no traps, we would expect like a positive number of complaints, right? Or at least maybe more complaints than if there were traps, right? And so maybe I think that a reasonable value is to center a prior on alpha at some, you know, smallish but not tiny number of complaints, saying that, like, you know, as a baseline, if we didn't set any traps, how many complaints would we expect to get, or something like that. And so I'm just going to use normal distributions here. Again, you'll see over the next few days why you might use different distributions for different things, but I do want to get through this example before noon. So let's say that we want to say, okay, we'll expect, sorry, go ahead. You could use it, well, a log normal would mean it has to be positive. But it doesn't logically have to be possible. It's overwhelmingly positive. It's overwhelmingly likely it's going to be positive, right? In other words, some building might have some weird thing going on. Like, I can't tell it that the reason I would rule, when I rule out that something's negative, it's because it's impossible for it to be negative. If I want to say it's overwhelmingly likely to not be negative, then I would just put a prior that's shifted far into that area. Because you want to allow yourself to be wrong in instances. But in this case, yeah, I would be astonished if that wasn't fine. But in theory, you want to be a little bit careful about ruling out things that aren't impossible, just unlikely. Because you don't want to, right? If anything that you put 0 probability on in the prior will still have 0 in the posterior. So you have to allow yourself to be wrong even just a little bit, typically. Unless it's like a logical constraint, like a correlation is between -1 and 1, by definition. I could if I wanted to, yeah. So here, let's say I wanted to say, I'm just going to, just as an example here, might not be the best choice. Let's say I wanted to say that at a baseline, we'll expect like, I don't know, 4 or 5 or some small thing. Then because this ends up going through like an exp, then I might do something like this. Right, remember, this is going to go through that exponentiation to the Poisson. So if I wanted to say that alpha is around, or sorry, that not on the log scale, that it's around 4 or something like that, or 5, then, but here I'm on the log scale. Does that make sense? If this wasn't a Poisson model, I wouldn't be thinking about it in this way. It's just because we have to then exponentiate things that I'm thinking about it this way. But you could just write like some number in here. But this was like my thought process, thinking about it a little bit like that. Again, I'm not going to spend too much time justifying these numbers. You're going to hear a lot of the next days about why I chose different priors for my analysis. You'll hear about reasoning about that. And then I'll put some relatively small standard deviation, I don't know, 2, or even 1, I guess. Remember, this is on the log scale, so these numbers are bigger. Or even 1. Again, this is actually only somewhat weakly informative. So this is, yeah, for here. Yeah, you're right. So I'm just showing you an example of something you do here. This is not making a super strong assumption that it's positive. It's just saying it's more likely to be positive than negative. If I wanted to go more extreme than that, which is probably justified, yeah, I would pull it, even pull it further away or reduce the standard deviation. Yep. So this is kind of like weakly informative in that sense, it's like, right? As opposed to highly informative. But if highly informative prior is justified in your area, then I don't think you should be scared of it. I think you should try to bring the knowledge that you have to the table. And then just for now, for the purposes, so this is how you would say that it has a normal distribution. For this purposes, let me see what I used in the other one so that you have it. I use negative, okay. Oops. So for here, this is just an example here. I said, okay, my prior, I think I'm gonna pull beta a little bit negative in my prior because as the number of traps increases, I would expect it to decrease the number of complaints about pests. Now, maybe that's a bad theory. That seems plausible to me. And again, I'm not focusing too much on these particular numbers. You should really think about your priors in the context of your area of expertise. This is just showing how you might write something that says, I expect it to be slightly negative, but I might be wrong. Having a standard deviation of 1 would allow that to be positive with not tiny probability, right? So this is just to show you, okay, how can I encode different types of beliefs here? Later, you'll see, well, I don't need to put numbers there. Those could be parameters that I want to learn about also, and that would be a hierarchical model. If I didn't specify it at 4 or 1 or whatever, and I said, make inference on those for me also, at a lower level of the model. The last piece of the model block here, then, is the Poisson distribution part, right? And again, there's a lot of ways to do this. The first thing I'll write, you don't have to type this yet. I'm going to type a few things that are correct, but that I'm not going to keep, which is a point. We could do this in a loop. We have n of them, right? Capital N of them. So we could do a loop like this, and then inside that, say that each one of them has a Poisson distribution with rate x of alpha plus beta times trap, right? So loop syntax in Stan is very similar to like most languages in R. But I'll show you the cleaner version, which is now I'll show you, well, two things. This one I'm not going to keep either. So in the document, this is eta, and the exp of it is lambda, right? Now, if you see the comment I wrote above a little bit, that Stan has some of these built-in functions that do that. So this Poisson underscore log says, if I change it to this, then I can get rid of, oops, what the hell did I just do? If I change it to that, then I can get rid of the x. What it's saying is, Stan is saying, okay, it's okay if you feed me in the input on the log scale, and I'll take it, I'll transform it for you internally. And that's often done more numerically stable, in a more numerically stable and efficient fashion when these sort of compound functions exist in Stan to use them. You'll see one like Bernoulli logit, which is like what you could use to do a logistic regression without having to do the inverse logit transformation yourself. It's essentially the outcome distribution and the link function, right? But either way, it's fun. You could also write this, or do it in a loop where you, sorry, not y. Our y is complaints. I'm sorry. I'm so used to thinking abstractly, right? Our outcome variable is complaints. Sorry about that. Is that clear? This actually looks pretty similar to the documents here, the document here, except the Poisson log distribution is letting us skip this middle step. And now, I'm going to hit this check button. And then it's going to tell me it's syntactically correct. If I had made a mistake, like forgotten a semicolon, which you may have noticed is required at the end of each line, unlike R, but like languages like C++, if I had checked that then, it would say parser expected semicolon. And then it would tell me, okay, before that symbol, which means I didn't end the line before it, right? So these are the sort of things that happen all the time. We try to make the error message informative, so this is pointing you to where there was like a missing semicolon, right? Or if I had, there's all sorts of things like that. So becoming a good Stan programmer is just as much about learning to write the code as it is about learning to quickly figure out how to interpret the messages. Some of them are easier than others because things get pretty complicated. But there's a nice thing in RStudio where we have synced it up with them, where this is this check button, so you don't have to compile it to see this. All right. Now, for this, in the name of time here, I'm going to skip the generated quantities block here, just for, and we'll fit the model. I was going to put some like code for prediction in there, which you'll see. It'll be up on the GitHub repo. But I want to make sure that we have time to fit the model and look at the results before the end of the half an hour. So did anybody, if you wrote a program like this and hit check and you have all sorts of errors, Lauren could come around, some people who are here can come around and take a look, but most people who are typing able to follow along with that? Good. I'm trusting you all. Okay. So I'm actually going to scroll down. I'm skipping some of the document here. Again, the document's pretty thorough. It goes through fake data checking, like we did in our in the workflow slides, but I want to actually fit this model, so I'm going to skip that right now. But you'll see the first part of the document simulates fake data from a Poisson. I'm going to go scroll down to fit with real data, which is at line 310 to me. But again, I wanted to include in the document the steps that I told you not to forget to do. So that is there in the beginning of the document. Later, as we get to more complicated models, I don't repeat it every time, although in practice I would repeat it every time. And so, okay, so what do I have here? I'm taking that data frame that I had in R called pest data, and I'm making a list where the names on the left correspond to the names I chose in the data block of my Stan program. Right, like if I had called n tomato instead, then I'd have to do this, right? In other words, I'm associating things in my R session with the names in the Stan program, right? So the traps column of the pest data, right, is a whole bunch of integers, and I'm saying that in the Stan program I told that was called traps. Yep. Sure. Yep. You could, if you knew you wanted to use these values, you could code them in the data block and pass them in, which would allow you to like iterate, like pass in different values for them. Yep. And so this is just one of the formats that Stan wants the data in. There's a couple different options. And so if I run that, oops. Shit. Can you guys change this this sampling line to shoot. I skipped a line that I wanted to show you. Let's do this. This will be good actually. So the way I've written the document, we first compile the model. We tell Stan, hey, translate this to C++ and compile it so that then we can run it. And so you can do it in 2 stages. You can compile it and then say, hey, run this and use this data. And earlier in the document, we compiled this model, but I kind of skipped over that due to lack of time. What I'll show you now is if we didn't want to do it in 2 stages, if you just wanted to say, hey, Stan, you do those stages for me, I'm not going to tell you first one and then the other. I'm just going to write, I'm not going to use this line. I'm going to use the Stan function. Sorry about that. I thought we were going to go a little bit through the beginning. And then I'm going to tell it what the name of my file is. And so I have it in the Stan programs folder, and it's called simple Poisson regression.stan. And then I'm going to tell it what data set I want to use. Now again, in the actual document, you could do it this way because it's already been compiled. And then I'm going to run that. And I'm going to leave it up there. What you'll see happening is nothing. And that's because it's doing the compilation step right now. And that takes a little while. And for simple models, the amount of time it takes to compile it dwarfs it's going to fit in less than a second. For complicated models, the compilation time is more negligible because of how long it takes to run this really complicated model. If we had compiled it earlier, we could have just run it instantaneously right now. But see there, now you didn't even notice when it's transitioned between compiling and fitting it, right? I'm gonna hang on a second, yep.
Hang on.
Is there a way to save the compiled version of the thing?
To save a compiled, yes and no.
I'm trying to run different things.
Yeah, so there's, when you reload in a new session saved stuff, there are certain things that can't be done anymore. And so it depends on, if you want to just fit the model again, then yes, I think you can do that. If you want to do certain more advanced things like get the gradient calculations like that, that's not going to work as much. That needs to be sitting in your session compiled during the session that you're doing it in. But yeah, for simpler cases, I think you should be able to do that. All right, so what did we get out of here? So this object here, the fit, again, now that I fit it like that, in the actual document, I'll leave the first version because that'll make sense there. But what I'm going to do is scroll down to I already put some R code in here, and I'm going to print alpha and beta. Now, we didn't have a chance in this. Yes?
Really quickly show the previous one that you wrote yourself.
This one?
The other bit that you did yourself, because we get errors.
Do you see that, Lauren? All right. Let me give it 1 sec if we can fix that so you can get on the same page. Were other people able to successfully compile and run this? Yeah? Okay, great. Yeah, so some of you might get, unfortunately, you might spit out compiler warnings that are totally irrelevant and ignorable, and there's a way to turn them off, but it depends on certain configurations on different computers. Those are not coming from Stan, those are coming from underlying C++ libraries that Stan is calling. And so if you are getting that and you want to turn them off, come find me or ask me in one of the question and answer sessions. I'm not going to take too much time away right now, but there is a way to turn those off. We have a document on the website somewhere about how do you turn those things off. So this output here, these are the things that I was estimating. You can ignore the LP thing for now. That's kind of irrelevant for what we're talking about now. The alpha and beta are the things we declared in the parameters block, right? And what this is telling, and so we didn't have time in our short little session here to go into all the details about Markov chain, Monte Carlo. There are lots of great case studies like on the Stan website to read more about how the algorithms work, but the point of using something like Stan is that we can't write down mathematically the things that we can't analytically solve those equations, and so we're gonna take samples, right, and describe probability distributions with sampling as opposed to by solving integrals by hand, right? And so what we get out are a bunch of alphas, a bunch of betas. Now by default, there are some settings we could have set when we ran it to specify how long we want to run it for, but what we get out are a bunch of values for alpha and a bunch of values for beta, and then we can summarize them, right? And so these are summaries. In other words, our estimate of the posterior mean of alpha is about 2.6. For beta, it's about minus 0.2, right? These are quantiles, like medians. And so these are summaries of the posterior distribution, summaries of what we now think about alpha after updating based on the data we observed, right? So this quantity here, I'm not going to talk about right now. So a lot of these things you can read about in more detail on the Stan website. The important thing here is to notice is that we get results, estimates for everything we declared in the parameters block. We would also get them for anything we put in the generated quantities, like predictions and things like that could get summarized here. But to really get a sense for what, like where these summaries come from, the next line like plots the actual raw, these are the posterior distributions of alpha and beta, right? So these are just, you know, histograms of all the samples that we got back from Stan. And for whatever parameters we can get, so these are what you would call like the marginal posterior of alpha. In other words, the posterior of just alpha. Right, we could view the posterior of alpha and beta as like a scatter plot, like a joint posterior distribution. But here we're just looking at the alpha part and just at the beta part. And so those numerical summaries are, if you took the mean of all the points that made up this histogram, you'd get that mean column, right? And if you found the median, you'd get what was in the median column. And so those are just summaries coming from the underlying draws that are coming out of here. And you'll see there's plenty of code. I'll show you, I'll do a little live time. What if we wanted to like look at the raw numbers? There's code later on demonstrating to do that in later examples in the document, right? But you see how I pulled out this thing? I could have done this as an intermediate step here and done like, I don't know, I'll call it posterior or something. And this command says, take out the samples and put them in a matrix. I could have said there's other structures that you can get them in, but this is saying put them in a matrix. And so what does that matrix look like? I'm just going to look at the first few rows. It's really just values of alpha and values of beta, and the number of rows is the number of times we told Stan to do it, which by default would result in this having 4,000 rows. But that's a parameter that you can set when you call Stan to run it. I mean, how long you need to run it depends on, well, in some sense, if you needed to get it to converge. But usually, if the model's working well, how long you run it for is just how precise do you need your, how many decimal places do you need your estimates to, right? The longer you run it, you can estimate like wider intervals or something with more precision, and you can, right? So that's really the only distinction. Once you know your model is working well, the longer you run it just gives you additional precision. Right, you'd have less on, now see, like I wouldn't normally look at like, it just prints it out with this many decimal places, but I don't actually care about that many decimal places. If I did, I'd run it a lot longer, and maybe even with this data set, I would never be justified in caring about that many decimal places, given how noisy this kind of data is. But if you're like an engineer or something like that, you have different kinds of data, you might need more samples, right? But really, it's just giving you back, fundamentally why we run Stan is to get back a bunch of numbers like this. Because, right, and then we can summarize these ways, these numbers, and to get the things that we care about, or feed them into predictions, right? This is, what should I think about alpha and beta given the model I specified and the data that I fed into it, right? And then if I want to say like, predict the number of complaints based on some number of traps, right? Then I could use these updated things, plug in the number of traps I want to predict for, right? And now simulate data, just like I did with the fake data simulation before, but if I do that using my updated values of alpha and beta instead of just sampling from the prior, then now I've actually made predictions from my model, right? In other words, the same process that you use to do the fake data simulations, you can use to do what are called like posterior predictive simulations. Except the difference is that on the one hand, you haven't learned anything from the data yet. I'm just simulating from my prior to investigate the implications of it. Whereas now I could use these values of alpha and beta are not just like randomly drawn from the prior, they're updated based on the data. These are my posterior. This is what I now think after I fit the model, right? So if I use these things in simulations, it's saying, well, what is the implication of my new set of knowledge, right? Not what's the implication of just the model that I wrote down. Yep. Depends on how computationally intensive what you're doing is. In theory, there's no reason not to use all of them. If you're doing something that takes forever or something, then you could sample a subset of them. It'll depend on, again, the more draws you use, right, the more precision you get. But yeah, ideally as many as possible, but in practice. Right, and so, I could have just used that too. Right, so this is alpha and beta. Now, in the 10 minutes left, so you'll see the next line of code here starts to do this posterior predictive checking. And that requires that we had coded in our model something that we didn't code in our model. So in the last 10 minutes, let's do that because it's really important. And then you guys later can run through the code and read all that. So the thing that we didn't code into our model, now I said if we could have coded like predictions down here, like for new traps, new whatever. But we also want to make in-sample predictions too. Ultimately, we probably want to make out-of-sample predictions. But we also want to make sure that we can make at least somewhat sensible in-sample predictions. In other words, we don't want to overfit the data. We don't want to say that our model can exactly replicate every little noisy detail of it. But just like we did before we fit the model, where we're saying, does our model yield reasonable data when we simulate from it? We also want to ask, after we fit the model, does our new updated model simulate reasonable data? And ideally, it would be more reasonable than the one before we fit the model, right? And so the idea of posterior predictive checking is exactly the same as this prior predictive stuff, the fake data simulation, except after fitting the model and getting a posterior distribution instead of just taking random draws from your prior, right? But you ask the same kinds of questions. Does the simulated data under my posterior capture the features that I care about for my problem, right? Not does it reproduce every little tiny detail and overfit or something like that, but does it fundamentally capture the important structure that I care about, right? In other words, like in this case, if we did predictions and it predicted that, you know, as we added more traps, like the number of complaints went down, that would be a bad sign. From that, we can already tell a bit because of the sign of beta, but in more complicated models, it's not necessarily so obvious based on one parameter's value what the implications are for the data, right? Here, it's a little easy, okay, beta's negative slope. But in really complicated models, the ones that you're probably wanting to fit eventually, it can be really hard to figure out like what one parameter means, right? But it's always easy to interpret simulated data, right? Because it's on the scale of the outcome that you're working with, right? And so understanding your model, I think, is fundamentally about simulating outcomes based on what you've learned about the unknowns. Not so much zooming in and over-interpreting every little thing about all your parameters, right? Now, it's not that you don't want to think about the right there on the log scale. Now we have to feed them into an exp, and it's a little bit tricky to think about what does beta mean here, right? Now, it's not horribly tricky in this case, but it's not the same as in a linear regression model, right? And then imagine even more complicated models than this with lots of levels of hierarchy and things. It can become unclear how to interpret one of the parameters, right? But if you just simulate outcome data, right, you always know how to interpret that because that's the data that's data that is a variable that you're studying, right? It's supposed to look like, in our case, the number of complaints or something. And so checking that your model is fitting well is not necessarily is the value of beta reasonable. It's also, does the combination of all the parameters in my complicated model result in plausible data, right? Because you have to imagine that you're usually in a scenario where it's harder than this to figure out how each little bit of the model is playing a role. And the way to do that is to see the results, the implications on the variable that you actually care about, right? For the most part, whenever I see a paper that has a huge table of regression coefficients, I just close it. Unless it's a super important paper. Because what I want to see is what are the implications for those estimates on the variables that we care about, not like what's your like convoluted interpretation in, I don't know, in some cases log odds or in this case just log and other things, right? I want to know, well, what does that mean for the outcome variable, right? You can, yes, figure it out, but it's not usually that obvious. And so if you think about the implications for the model on the outcome variable, then the only thing you need to do is just to simulate it. And this is like the beauty of this like generative process, is that all the questions you want to answer you can do by simulating. By saying, here are the implications of my model because we've defined at each point on the way a probability distribution, right? And so in order to do that, now I'm going to code up in-sample predictions here that get checked against the observed data. Again, not to capture every little tiny bit of noise, but to capture the like fundamentally like scientifically important features of the data. But coding up out-of-sample predictions is exactly the same, except you would be passing in new data instead of the actual code looks exactly the same, right? And so keeping with the convention that I guess Andrew Gelman started for in-sample predictions, I'm going to use, now again, in my generated quantities block, I'm going to generate a variable that has the exact same size and structure and type as my outcome variable, but it's going to be simulated data. And Andrew calls this like Y rep. Or in this case, it could have been complaints rep. In other words, like replicated, which kind of means like in sample or something. I don't know it's just a convention, but you're going to see it, so we might as well get comfortable with it. For out-of-sample predictions, you might, I forget what I think he uses like Y tilde or something, or some other symbol. But again, this is like common, so I'm using it here. So this is going to be, like essentially attempting to replicate the important features of the observed data, not every little tiny bit of noise. And then the coding of this is really easy because essentially we're going to say exactly what we said in the model block, but instead of just telling it the name of the distribution that we want it to have, in this case the Poisson distribution with log link, we're going to tell it to draw random numbers from that distribution. In other words, we're going to explicitly use a function that is a random number generator, and we're going to feed into it the posterior distribution of alpha and the posterior distribution of beta. We could also do this in R after the fact by like extracting that matrix, right? So like in the generated quantities block, we're saying, okay, like assume now that the model's been fit and that, right? This is just a way of doing it within the Stan program instead of extracting it in R. But, yep. Do you prefer to have things in the same file or multiple files? It's kind of, if you're doing loops and stuff, it's going to be faster to do it in Stan because they get their C++ under the hood. But the stuff in generated quantities is pretty efficient in general because it's not MCMC. It's just now Monte Carlo. You can just use like the R norm function in R Pois for the Poisson. So those are actually really efficient as opposed to doing like Markov chain Monte Carlo stuff. All right, in our last 2 minutes here, we'll write this line of code so that when you run the document later, it actually works. Now, wait, are you doing vectorized RNGs or who's working on that? Somebody is working on vectorizing all the random number generators in Stan. For the moment, we have to write it in a loop, although that doesn't affect the speed, really. It's because it's C++ under the hood. So here I had a vectorized version where I didn't have to loop over the number of observations. But down here, I'm actually going to loop over the observations, which is just a syntactical thing here until there's vectorized code. And then, now instead of saying that complaints has this distribution, now I'm going to do an assignment. I'm going to say, simulate a number and assign it to one of the slots in this Y rep, right? So I'm not going to use this notation anymore. I'm going to say like, okay, the little nth thing is equal to something. It's going to be equal to some simulation. Right? And so in our case, this is why I put this little function at the top for you guys. I'm going to just copy the name of that. Now, what I really would be what I recommend you use, like starting in like, I don't know, the next version of Stan or whenever the next one comes out, is just the built-in Poisson log RNG. In other words, it's exactly this, and you just tack on the RNG for random number generator at the end. But when I ran the program using that, occasionally at the beginning of the Markov chains, before it's gotten to a reasonable spot in the parameter space, it gets some weird values, and then it goes into the Poisson and simulates something crazy, and there can be some numerical problems, and so this just avoids that. But for most problems, this wouldn't even be necessary currently. I think it's something about this particular data. But anyway, the point here is just that functions that end in the RNG suffix do random number generation. And so if we had a normal distribution, it would be normal underscore RNG. And if we were using a binomial distribution, it would be binomial underscore RNG. So all of the random number generators in Stan are always going to end in an RNG suffix. And then the only thing we need to do here is, again, put in this thing, except because we're doing it, so I copied and pasted from here. Because we're doing it in a loop, we just need to index the traps. instead of passing in, otherwise it would use the whole traps vector at every iteration of the loop. And again, this is only because there's not a vectorized form of, I think pretty soon you'll just be able to do this. You know, blah, blah, blah. That's just because I'm not typing out the full function name, just like that without having to loop. Unfortunately, that's just the state of the code base because we have limited humans working on it. But so what this is going to do then, right, so just in the last 1 minute, when you run this later, what you'll find is that, so this is going to generate capital N, or 120 in our case, because that's the size of the data set, simulations each time the program is run, right? For each value of N, it's going to simulate a value of complaints, or Y rep here, based on the posterior of alpha and beta, right? And so capital N is 120, so Y rep is going to have the same size as Y, except we're doing it for every value of alpha and beta, right? This program is actually run at each step along in the posterior that we have a sample from. And so what we end up with actually now is, right, so here was that matrix of alpha and betas, and right, we had, like, actually there's like 4,000 of them. We're gonna get 4,000 simulations of that size 120 vector or integer array. In other words, for each value of alpha and beta, in other words, it does this whole thing. So that means you get, right? So that means it'll have, like, when it uses this value of alpha and beta, it's going to simulate capital N of them. And when it uses the next value of alpha and beta, it's going to simulate capital N of them, right? So every time it's simulating a whole data set, right? In other words, what does a whole data set look like with this alpha and this beta, right? But then by doing that for each value of alpha and beta, you now get a distribution of data sets. We got to stop. It's lunchtime. You get a distribution of data sets, and that's what the next piece of the document is going to cover. How do we look at that distribution of data sets and compare it to the data we have and check if it captures important features of it? All right, and then feel free to ask me questions over the next few days if you're looking at the rest of the document, or email me after the course if you go through and try to do the more advanced sections of the document.